We have a lot of people listening. And if you didn't hear that, I was talking over it, sorry about that. This meeting is recorded. We will hope to broadcast this afterwards. Oh, it looks like there are many more people here than I had thought. Wow, awesome.
Hi, Becky.
Hey, Becky.
Hey, everybody. Sorry, I was trying to figure out the Zoom thing. It routed me, like, in a weird way that Zoom normally doesn't. So that's why I was like, what am I doing wrong?
By the time we get this electronics thing figured out, we'll be able to meet face-to-face again.
Of course.
Yeah, so we're given just a minute or two more for anyone joining. If they just clicked the link and they did what my computer did when I joined and decided to open Zoom in the browser and in the app, and the Wi-Fi was a little wonky, so now things seem to be smooth. I appreciate everyone joining and muting. This should be able to take off instantly. Yeah. So let's go ahead and get started. I think if anyone joins, we'll be rebroadcasting this at some point and just share all of this stuff because I can't help myself but to share my love of space and everything that I run into with it. So hello and welcome to the June meeting of the Berks County Amateur Astronomical Society. We're based in Berks County here in Pennsylvania, halfway between Harrisburg and Philly, but online we can be anywhere around the world. So we're hoping to reach out around the world and, well, literally reach out. Well, we're taking photons in all the time from everywhere. So I'm excited about space, all the stuff that we get to see, the things we get to do, and all the exciting new things happening. There have been a few rocket launches. Of course, I always like to talk about space traffic. The Starlink satellites went up without a hitch. There will be more about light pollution in all of its forms at some other meeting. But if you don't know, I have this radio thing and I talk on WEEU and I try to bring as much space content as I can to it. More on that at some other time, but they were able to fly me down to see the SpaceX launch with Crew Dragon. Bob Behnken and Doug Hurley are still on the International Space Station. We're all excited that they used this new system to get there. Now they're sort of in the thick of research. There's just more crew on board to help alleviate the workload of the other astronauts of Expedition 63. So more exciting things from them. Keep your eyes out for any space station news, any launch news. There should be a rocket launch tonight, shortly after midnight from Rocket Lab coming out of New Zealand. Rocket Lab is a US company joint with New Zealand, but they did just build a launch pad in the Mars facility in Virginia. So more rocket launches, more stuff, more research. James Webb is a little delayed, but more to happen, more to come. At the end of our meeting, we're going to talk a little bit more about our star parties coming up. It's possible to socially distance and have a star party. You can even zoom in from somewhere. I'm talking with a couple folks, a couple chasmoners who might be broadcasting live views from their scopes. So more on that later. And Barb will fill us in on some dates at the end of the meeting. But right now, I'd like to welcome our speaker for our meeting, Mark Kochte of the Applied Physics Laboratory coming out of Johns Hopkins, is that correct? And without further ado, he's going to tell us a little bit about the New Horizons mission. And so Mark, thanks for joining us and take it away. Everyone, if you please mute your microphones. Yes, go ahead.
Someone was going to say something? No, all right. Good evening, everyone. My name is Mark Kochte. I work at the Johns Hopkins University Applied Physics Lab in Laurel, Maryland. I am a mission analyst on the New Horizons mission. And tonight, I'm going to be presenting to you basically an overview of the solar system and exploration of the Kuiper Belt, all done by New Horizons, the latter half of this anyhow. So I'll start sharing my screen here. Can you guys see my screen? Excellent, excellent. Okay, great. That's not what I wanted to have there. Let's try this again. All right, so welcome to New Horizons. Just to make sure we're all on the same page with everything, I want to talk about our solar system, just to give you a primer on our solar system first, and then we'll go into the Kuiper Belt. So our solar system is a very complex entity. There's a star in the center of it, and it has some rocky worlds orbiting it. It has some gas giants orbiting it. It has some ice worlds orbiting it, and it has a lot of debris orbiting it. And while we've found thousands of other exoplanet solar systems around us in our galaxy, not one of them is an analog to our solar system. So at this point in time, our solar system is unique to everything we've seen out there. At some point, we expect to find analogs to what we have, but right now, we are the only one like this. So our solar system seems to be geographically easily broken up into 3 zones. Zone 1 would be the inner zone. The rocky worlds exist here: Mercury, Venus, Earth, and Mars. And it extends basically from the sun to the asteroid belt. Zone 2 extends from the asteroid belt out to just past Neptune's orbit, or the Kuiper Belt. And it is composed of the gas giants, or the Jovians, Jupiter, Saturn, Neptune, and Uranus, or Uranus, Neptune in that order, plus all the debris in between. Then zone 3 is the least known zone of the 3 zones. It's the outer part of the solar system as we know it at this time. There may be a zone 4, but we have no data to speculate about there being one out there. At this point, zones 1, 2, and 3 are what we have. And zone 3 is basically comprised of the Kuiper Belt. It was first proposed, the Kuiper Belt was first proposed by Gerard Kuiper in the 1950s. And the first object to be detected out there beyond Pluto's orbit was in 1992. So 40 years later, after he proposed that there was an area out there of material, we start finding things. This Kuiper Belt is basically a large donut-shaped region that contains objects so far that we've been able to detect from 10 to 2,300 kilometers in size. There are undoubtedly smaller objects out there, but we just have not been able to see them, given what we have, the capabilities we have here on Earth to look out there. It extends from 30 to 55 astronomical units out from the sun, where 1 AU, or 1 astronomical unit, is the mean Earth-Sun distance, or 93 million miles. So the Kuiper Belt extends 30 to 55 times further away from the sun than we do from the sun. And who knows what's all out there? So basically, in a graphic depiction, this is the zones. Zone 1's in the intersection here. Zone 2 in the blue. Zone 3 pushes outwards. Now, we've been doing a lot of exploring of the solar system. The inner part, Zone 1, has seen a great many missions, especially to Venus and Mars. Zone 2 has seen a fair number of missions. And Zone 3, up until New Horizons started exploring it, has not seen a dedicated mission to explore the Kuiper Belt. The Pioneer spacecraft and the Voyager spacecraft have flown through it, but they weren't designed to actually explore that portion of our solar system. So again, the Kuiper Belt, it's very far away. If you were to ride a bike at average 12 miles an hour, it will take you a little while to get there. Not quite as long. Space Shuttle, when it was flying, would take 25 years, but New Horizons, when we sent it, took 9.5 years just to get to the inner part of the Kuiper Belt. So besides Pluto, there's a number of other largest Kuiper Belts, or KBOs, Kuiper Belt objects, KBOs, that were discovered in the 90s and the 2000s. Notably, these would be Haumea, Makemake, Eris, Quaoar, Sedna, Orcus, Ixion, among others. In 2006, the IAU, the International Astronomical Union, visited the definition of what a planet is and redesignated Pluto from being a planet to a dwarf planet. So basically, dwarf planet is a subset of what a planet is. Gas giants are a subset of a planet, and rocky worlds are a subset of planet. So it's not a demotion, it's just a reclassification. If we wanted to talk about this in full detail, I have a completely different talk for a whole nother time that would easily take an hour or better to go through. So, what do we know about the Kuiper Belt? Well, like I said, it's about the shape and size of the asteroid belt, not size, but shape of the asteroid belt, but it's 20 times as wide and about 20 to 200 times more massive than the asteroid belt. The asteroid belt is made of rocky material, rocky bodies, while the Kuiper Belt is made of icy bodies. So the Kuiper Belt exploration craft is the New Horizons spacecraft. As you can see here, names and acronyms around the spacecraft here point to the different instrumentation, different instruments on it. And you can see a couple of people right here next to the spacecraft in the clean room. So you can see the size of this is basically about the size of a baby grand piano. Getting to New Horizons from Voyager took a number of years and a number of heartbreak missions. Pluto 350 was proposed, and Mariner Mark 2, and Pluto Fast Flyby, and the Pluto Express either were approved and then canceled or were just not funded until New Horizons came along. Alan Stern down here in the corner is the principal investigator who's in charge of the New Horizons mission, and he is one of the members of the Pluto Underground who is responsible for all these attempts until we finally got going with Pluto. So the spacecraft was built at the Johns Hopkins University Applied Physics Laboratory. It had the size of a baby grand piano. You can see a bunch of people around it while it's being assembled. This black tube here is the radioisotope thermoelectric generator, or the RTG. It's our little nuclear power plant that powers everything on the spacecraft. It has enough plutonium, ironically it's plutonium we're using, to power the spacecraft until the 2030s, after which the spacecraft will no longer have power and it will just quietly fade into the universe. There are 7 science instruments on board the spacecraft, and they mass less than 1 camera did on the Cassini spacecraft, which orbited Saturn. These are the science instruments on New Horizons: Rex, Ralph, Alice, Lori, Swap, SDC. SDC is the Student Dust Collector. What's notable about SDC is that it is the only instrument that's flying on a spacecraft that was completely designed and built by students. And at the time, they were high school students. When they built and gave it to NASA to put on the New Horizons, a number of them went off to college and got their degrees and PhDs based on the data they collected from their instruments. And it is still going strong. So in our exploration of the Kuiper Belt, first stop was Pluto, the whole Pluto system. That was the main focus of the mission. Everything after that is icing on the cake. So the Pluto system, we know, has 5 companions. Charon was discovered in 1978. Then in 2005, the year before we launched New Horizons, 2 small moons, Nix and Hydra, were discovered. Then while New Horizons was on its way out to Pluto, we discovered Cerberus and then Styx. And people got very concerned about there being other things orbiting around Pluto that we might hit. So we had a campaign while we were approaching the Pluto system of studying the space around Pluto to see if we could detect anything else. And happily, we didn't detect anything because hopefully there was nothing there to detect. If there was anything else, we never saw it and we never encountered it. So Pluto is very far away, and it's very, very faint. It's what astronomers would say it's about 14th magnitude in brightness. And to give you an idea of what the brightness is, the sun is minus 26. So the smaller the number into the negative, the brighter the object is. So the full moon is minus 12 magnitude. Venus, which was in the evening sky for the last few months, is around minus 4. The morning sky right now, Jupiter is shining at minus 2. Many of the stars that you would see just going out at night are 0, first magnitude, second magnitude, third magnitude. Pluto is 14th magnitude. The numbers that you see here are magnitudes of all these other stars. For those of you who are unfamiliar, if you were to go out to a very, very dark site, like in the middle of the desert, and you're fully dark adapted, your eye can go down to 6th magnitude. Some people can see down to 7th magnitude, but that's it. You need to have a telescope to be able to even see Pluto. And if you do, you're not going to be able to differentiate it from the background stars unless you have a really good
Oh.
Oh, Hubble. Hubble has brought us a fantastic view of the universe. We've seen amazing galaxies, stellar clusters, gas clouds, all kinds of things. It's really turned our view of the universe on its side and given us fantastic understanding. However, when we look at Pluto, this is what we see. It's a bit blurry. It's because Pluto is small compared to everything else that Hubble looks at. We go back, these dust clouds, these star clusters, they take up an area of the sky. Even if it's a small area of the sky, they take up an area, and Hubble can capitalize on that. Each of these dots here is about the apparent size of Pluto, and that's the best we can see. So this is back in the mid-90s. We could do deconvolution on this, and we can see shadows and light areas on Pluto that are there. But this is the best we can do. Each pixel here, each little square that you see, is about 300 miles across. So we aren't going to be picking out any Plutonian license plates from these images. In 2010, Hubble got its last servicing mission, and the Advanced Chemical Surveys was put on there. And this is what we were able to get with Hubble. And you can see the shadowed areas have a definitive form, and the light areas also have a definitive form. But again, this is the best we could see. So, from a spacecraft, this is from Cassini, right about the time that New Horizons flew past Pluto. For those, I've got a poll here to give you guys. So you bring it up. Instead of guessing which one of these is Pluto, I'll let you select from one of these 6. Now, I'll let you take a moment and you select which one you want. You guys see the poll?
Okay.
Everyone's voted if they want. No one likes 6. One person likes 6. Excellent. Okay. We'll end the poll. A lot of people like number 2 as being Pluto, but I'm going to have to disappoint you. And it was number 5 was Pluto. So the 6 people who thought that was Pluto, congratulations, you guys are better than mine. But Laura, you might want to mute.
I'm trying to.
Okay, moving on. So when we flew past Pluto, through the Pluto system, this is July 2015. This is the trajectory that we took through there, and there's the timestamps of the times when we flew past. And as you can see, we flew flew through the shadow of Pluto here and of Charon here.
Of the season that we're heading toward, you know, and just
on the approach, the month out, we were looking at Pluto to see what we could see, and these were the images we were getting with New Horizons, which are better than what Hubble was able to get. So about a month out, we were already exceeding what Hubble could do. And then a week out, we saw this. And then a few days out, this is the backside of Pluto. As we were approaching Pluto, it was rotating. It rotates every 6 and a fraction day. So this is the backside of Pluto that we did not see during the flyby. This is the best we have of that part. This was the side that we flew past. Now, all these colors here are real, but they've been enhanced so you can see the differentiation. Overall, the planet has more of a rusty tannish color. This is some of the terrain features that have been named. The Sputnik Planitia here is the large nitrogen glacier on Pluto. Hillary Montes, the Tenzing Montes are some of the tallest mountains on Pluto. In fact, the Tenzing Montes has the tallest mountain on Pluto, which caps out around, it's somewhere between 11 and 12,000 feet. So the mountains here are on par with the Rocky Mountains in
John Ossoff has been declared the winner.
So some stats from the flyby. We launched in 2006. 9.5 years later, we did the flyby. We traveled 3.1 billion miles. We have a speed of 32,000 miles an hour, or we're traveling 3 times the Earth-Sun distance every year. Our target box that we were to fly through when we did the flyby of Pluto was about 60 to 90 miles across, and we flew through a point 26 miles off of the center of that box. To give you an idea how accurate that is with our nav team, it would be the equivalent of shooting an arrow from New York City to Los Angeles, hitting the eye of a statue, shooting a second arrow, splitting the first arrow, shooting a third arrow, and missing by 1/4 of a millimeter. That's how accurate we were. We arrived about 88 seconds earlier than we had thought, but given that we had this planned out for 9.5 years, 88 seconds is really pretty good, and we had accounted for this. And we were about 12,500 kilometers above the surface of Pluto when we went past. Charon was on the far side of Pluto from us, so we didn't get as high resolution images of Charon as we did Pluto. So Pluto, the highest resolution images we have were 80 meters to a pixel, whereas Charon was 800 meters to a pixel. Here's a shot of the Sputnik Planum, the giant nitrogen glacier. A little close-up view. You can see some of the ice flows on the glacier, some of the mountain region next to the glacier, the Tenzing Montes right there. The highest mountain is this peak right here. Some cryovolcanoes at the terminator of the day-night transition point. The Tenzing Montes are up in this area. And a frozen methane lake in another set of mountains, the Al Adrizi Mountains. And Pluto has an atmosphere. If you weren't aware, there's a nice atmosphere on Pluto. It's super thin. It verges on a vacuum. However, there's still enough material here that this is not JPEG artifact, but these are haze layers in the atmosphere, and it extends outwards of about 1,000 kilometers. So how we can measure this was when we flew behind Pluto, we could take, we had detections of the sun, and we could see how it faded out until we went behind Pluto, and then we had no detection, and then it faded back into sight again. When we flew behind Charon, we could see the sun, and then we couldn't see the sun, and then we could see the sun again. So there's no atmosphere on Charon, surprisingly, given that Pluto has one. So talk about Charon real quick. Charon was discovered in 1978 by this gentleman right here. It was named after the boatman for the River Styx, given that Pluto is the god of the underworld. This bump right here is Charon that was discovered. And it had been observed many times before Christie here decided that this was an actual feature. other astronomers that studied Pluto said, oh, I've got an instrument effect. I'll throw that observation away because this is what I'm looking to see. Jim Christie said, this thing pops up every 6.5 days. It has to be something real. So they did deeper studies of it and found that, yeah, there's a moon around Pluto. Turns out, however, that Charon is, while it's half the size and eighth the mass of Pluto, it's still massive enough that the center point for the orbit is between Pluto and Charon. It's not within the crust of Pluto. So actually, this is a binary system because they don't orbit each other. They orbit a common point between. Now you can see examples of how large Charon and Pluto are compared to Australia and the United States here to the right. So this is about a month out view of Charon. The original image from New Horizons and a deconvolved image. We can see a darkish area towards the top and a little bit of features, but not very clearly down below. Closest approach, the darkish area here is this brownish reddish area at the top. And the rest of it is a pretty uniform gray. Some of the features that have been named on Charon here, you see a number of the craters, some of the rift canyons, and the other members of the Pluto system are the moons Hydra, Nix, Cerberus, and Styx. Again, Hydra and Nix were discovered the year before we launched. So we knew they were out there. They're about 30, 35 miles long. Cerberus was discovered in 2011. Styx, which is like 9 or 10 kilometers at the best, was discovered in 2011 for Cerberus, 2012 for Styx. So those were the best images we have of Pluto's other moons. Once we were past Pluto, we still had things to do. Other than dumping data down, we still had exploration to do. So these yellow dots here are all Kuiper Belt objects that we could see with New Horizons. Ixion, Quaoar, Photis, 2000 KX14, Huya, 2000 MS4, 2014 QE34. And then this box here are a number of Kuiper Belt objects that we passed relatively close to. Relatively close to meaning we were still millions of miles away from them. So we didn't see a lot of detail, but we could get some information on them. However, our main goal right after the Pluto flyby was to go visit MU69. It was discovered a year before the flyby by Hubble, but we didn't decide to target going after it until after the Pluto flyby. We had enough to deal with just planning for Pluto flyby. However, going after this thing, or going after anything that far out at this point in time of the mission is hard. I don't know how to explain how difficult it is. The flight ephemeris is uncertain. We could only see MU69 with Hubble. No ground-based telescope could see MU69. So we could only use Hubble data to try and plot the orbit. And there's a lot of uncertainty in that. We didn't know if there's any moons around it. We didn't know if there's any debris field around it. The light levels are so much lower that far out. It's 44 astronomical units away from the sun instead of 33 where Pluto is. So the light is half as bright as at Pluto. We were going to be we planned to fly much closer to this object than we did Pluto because, well, one, it was smaller. So we were planning to fly like 3 times closer. The object, the best we could determine from ground-based observations, which I will talk about in just a moment, was it's about the size of Cerberus and Nix, the moons of Pluto. Not much larger. Actually, it's not larger than those. It's a little bit smaller. Also, radio waves travel at the speed of light. So the further out we go into the deep solar system, the longer it takes signals to travel out to the spacecraft and to come back. When we flew past Pluto, we had what we call a round-trip light time. When we send a signal out to the spacecraft and then get a response back, the round-trip light time was about 9 hours. At MU69, it was going to be over 12 hours. so we could send the signal to the spacecraft. It would be over 12 hours before we would get a response back. So we really had to pre-plan where the spacecraft was going and pointing. Plus, the spacecraft had been going for a number of years, and it's getting older. We had less power because the plutonium is depleting. And we also had a smaller budget to work with to make all this happen. So when we left Pluto, we decided to go after MU-69. There were several candidates that the science team had before them to choose, and they ultimately chose MU-69. So we began doing these TCM maneuvers, these trajectory correction maneuvers to change the course of the spacecraft ever so slightly. So TCM 20 was done shortly after the Pluto flyby. TCM 22, 24, and 26 were done here. 21, 23, 25 were actually not performed. So this was the flyby time, and that was on January 1st last year. A couple months out, we started looking to see if we could detect anything in this space around MU-69. Now, mind you, MU-69 for us was still a point of light that didn't even fill a pixel on the cameras. We were hoping that if we found anything, they would be large enough to reflect enough sunlight that we could detect it. Barring that, we hoped there was nothing out there, which is why we wouldn't detect anything. Complicating everything for us was the background of behind MU-69 was the Milky Way. And that's where we were looking to find MU-69 and look for these debris fields that may or may not exist around it. Super, super, super difficult to try and track that. And mind you, we're still trying to zero in on flying past this object. The best way we could do optical navigation with the spacecraft was to take multiple images of this star field, subtract out all the stars all the objects that did not move, which would be all the background stars. And we would have MU-69 right here on the right. So give you, again, another idea, huge star field that we're looking down, and this is MU-69 from that star field. This is Hubble images here on the right. Again, it was discovered, the object was discovered in 2014. It is magnitude 27. Remember, Pluto is magnitude 14. We took a number of Hubble images and stacked them together to be able to pull this out of the noise. And you can see, as from the different Hubble images 10 minutes apart, MU-69 popping through here. This is one of the smallest known KBOs to date. Again, we know there's smaller ones out there, we just have never seen them. The orbital inclination and the low eccentricity of the orbit strongly suggests this is a remnant from when the solar system first formed 4.6 billion years ago. Spectral observations from Hubble suggested that it has a very reddish color. And we were estimating that it was just under a 300-year orbit around the sun. So I mentioned earlier observations from Earth of MU-69, but I also said that we could not see MU-69 from Earth. So what we did we did occultation studies, and occultations are when an object passes in front of another object. So when you have an eclipse of the moon or the sun, basically you're seeing the effect of one object passing in front of the other. So a total solar eclipse is when the moon passes in front of the sun. It occults the sun. For people who study asteroids, and there's a whole group of folks that do this, known as IOTA, the International Occultation and Timing Association, they study when asteroids pass in front of background stars and can get a shape model of the asteroid. So the asteroid here is going to pass in front of the star that's out here and cast this shadow across Earth's surface. So they will set a battery of observers up perpendicular to the flight path of the shadow. And you can see each line here is an observer. And this observer never saw the star wink out. When the asteroid passes in front of the star, it will briefly dim and then it will brighten back up again as the asteroid moves on. So this guy saw nothing. These folks all saw something, and this is the time that the star disappeared. So these folks had a longer time of disappearance than these folks. So you can draw a rough shape of the asteroid from these occultation studies. So this is how we did it with MU-69 from the ground, from Earth. We had 3 opportunities in 2017 and another opportunity in 2018 to do occultation studies. One of the occultation studies had to use the Sophia aircraft to fly over the South Pacific. So we had a June 3rd, July 10th, July 17th, 2017, and August 4th, 2018. Those are from Colombia and Senegal. This image down here shows the shadow path of the occultations for the 2017 events. So 2017, the first one was here, and we got nothing out of it. We had a complete miss on the shadow path because we really didn't have a good feel for the orbital parameters of the object. The Sophia aircraft on July 10th picked up something here, but it was way off from where we suspected the asteroid would, or the Kuiper Belt object would be. So we weren't sure what this was, but maybe it was a moon, but we didn't know. Then the July 17th attempt got multiple hits. All these lines here are individual telescopes that were set up, and this is the spot right here that we got dropouts of the star. So you fill it in, we have basically what we see is a global object. But we can't tell if this is 2 objects that are orbiting very closely together, or if these are 2 objects that have merged together. We would find that out when we flew past. But this was our first clue as to the shape of what we were about to encounter. So on the way in, we had to call it something other than MU-69 just because people like to name things. So we came up with the formal name of Ultima Thule, basically meaning the furthest most land away, since this is the furthest most object that we would ever fly past. And then after the flyby happened this past November, the official name of Arakoth was granted to MU-69. It's a Powhatan Algonquin word that means sky. And the name Arakoth basically reflects the inspiration of looking at the skies and wondering about the stars and the world beyond. The science team approached the Pamunkey tribe, which is part of the original Powhatan Confederacy, to ask permission to use the name of Arakoth for MU-69, and this was granted by the tribe. In November 2016, Reverend Nick Miles, the gentleman right here, performed a traditional Algonquin song at the naming ceremony of MU-69. So back to our object. Our closest approach happened at 12:33 a.m. on January 1st. So 33 minutes after the New Year, we had a second celebration. First the New Year celebration, then the flyby celebration. However, the round trip light time is over 12 hours, so we wouldn't have any data from the spacecraft for almost 10 hours, given the spacecraft was going to be studying, taking images and studying the environment around MU-69. It could not also transmit information back. So it would have to perform all its studies and then at a prescribed time after the flyby, start transmitting data back. So it was around 10 in the morning before we got our first sight of what MU-69 looked like. We flew past it at 32,000 miles an hour still. This velocity is such that you could go from Reading, Pennsylvania to Philadelphia in just over 6 seconds. So we took our first images of MU-69 late in August 2018. Again, our approach was 3 times closer than Pluto. We were 2,200 miles away from the object. The best resolution images we have give pixel down to the length of a football or a basketball court. And as I mentioned, this is the most distant flyby in spacecraft history. This is what we call the B plane. The object is here. We hit our aim point right here. We were off by just a few kilometers from this aim point, and we arrived at the aim point just a few seconds later than we had originally planned. This is the trajectory relative to MU69. Notice we did not go through the shadow. It just wasn't going to be an option. So we did not do a look back to see if there's atmosphere there. But given the size of it and given what we could study from the approach, we don't believe there's an atmosphere around MU69. Our first observations were here. We start doing op-nav imaging here. We had the closest approach right here. This purple diamond was the solar conjunction that happened 3-4 days after our closest approach, where we'd have no contact with the spacecraft for almost a week. And then afterwards, we started dumping the data, and we are still dumping data down from the flyby. The data rates are really, really low. This is the timeline of days leading up to the closest approach and a few days after. The blue diamonds here represent data dumps from the spacecraft. We had 2 data dumps right here just before the closest approach in case something happened to New Horizons and we hit something at 32,000 miles an hour, it was going to hurt. So we wanted to make sure we got at least something. So the first 2 diamonds there are the first images that we dumped down. And then the following 3 diamonds are the next set of images that we were able to dump down before we went into solar conjunction. To give you an idea, again, how close we were just under the width of the United States in distance for flyby. And here is MU69 compared to Earth. So about a day out, this is what we could see. It went from something that was a sub-pixel to 3 days out, it was a pixel, to 2 days out, it was 2 pixels, to 1 day out, it was now a shape. And then we were able to measure a rotation of that shape. And we measured initially, we were estimating it's about 15 hours to were rotated on its axis, give or take about an hour. We now understand it's about 15.9 hours. So on the left is the approach images, on the right is the normalized images of the same. So you can see what we were seeing in the rotation and how the resolution got better and better as we closed in. And color. The MVIT camera was able to do a color map of the object, and it pretty much is a uniform rusty tan red all the way across. There are bright spots along it, notably here and here in this depression, some brightest there, and in the neck region between the two, it's fairly bright there also. But the rest of the object is fairly uniform in shape. So this is 30 minutes out, 19 minutes out, 7 minutes out, 6.5 minutes out. And you can see little pock marks of craters all around in here, up in here, over here, there. It's believed this is also a crater, but there's a possibility it may not be a crater, but it may be a collapse feature. And this is the departure image that we just saw the outline of, the crescent view of MU69. Now this crescent view actually told us that this object was not round. We had suspected these 2 lobes would be spherical in shape, but they turned out to be not. And I'll cover those in a moment. Cutting back to ground here, those of you who know who Brian May is, well, let me rephrase this. Those of you who do not know who Brian May is the gentleman here with the hair. He is the lead guitarist for the music group Queen, and he is an astrophysicist. He did his PhD studying the zodiacal light dust particles in the solar system, in the orbital plane of the solar system. And he is a member of our science team. he came to the Mission Operations Center and got a tour of our mock, the Mission Operations Center. And as a little fun thing, the woman here, Becca, she was the lead flight operator. And we were getting ready to do what we call a pass with the spacecraft, where we would be doing a communication connection with the spacecraft and downlinking some data. Well, now we're a couple days out from the flyby at this point. While he was doing the tour, the time for the pass was coming close. And what we have to do is we have to talk to the Deep Space Network, which there are several stations around the world that talk to all this spacecraft in the solar system. And we do a preliminary, you need to set this station to this point and this frequency and point it at this coordinate system. A preliminary pass briefing with Deep Space Network. Typically that's done by the flight operator, which Becca is one. But she decided to have Brian May do the pre-pass briefing. So we did a few rehearsals with him, and then during the briefing, when the Deep Space Network called to get the information, he gave it all, very professional, very straightforward, and everything was well done. We had a nice little laugh, and someone in the group said, I wonder if the Deep Space Network even realizes who that was. That moment the phone rang, and we put it on speaker, and it was a guy from the Deep Space Network that says, was that Brian May? Anyway, that was my humor. I can't hear if you guys are even laughing. One of the things Brian does is stereoscopic imaging. And this is one of the things he brings to the team. This is an image pair done by him. If you're able to cross your eyes or look past it, you can make these merge together and get a stereo image of Arikoff here. I can't do that, but some people can. So I'll leave it here for just a moment and let you play with your cross-eyedness while I take a drink. So I hope some of you could see it. Moving on, here's the size of MU-69 compared to the mountains on Pluto. You see, it's fairly sizable, even though it's a tiny little object. So some of the flyby stats. We traveled 4 billion miles to get here. We had a speed of 32,000 miles on the flyby. We were a couple seconds late on the timing, but we had a plus or minus 9-second uncertainty bracket to work in. We passed within 2,200 miles of it. We have 50 gigabits of high resolution images, compositional spectroscopy, temperature measurements, and a slew of other data that we collected just from the flyby alone. Our data rates are abysmally slow. We're 800 bits a second and dropping. For those of you who remember dial-up modems from the 90s, when you had 2400 baud modems, that's fast compared to what we're getting now. So what we've learned with Arikoff, it's approximately 33 kilometers by 18 kilometers, which puts it on par with Nixon Hydra. Nixon Hydra at Pluto, had a rotation rate of 15.9 hours. If it was rotating much faster than that, it would fly apart. It orbits the sun every 297 years, at an average distance of 44.6 astronomical units away. It's a completely reddish, rusty, brownish color. There is no atmosphere. There's no magnetic field. There's no evidence of moons or rings. Temperature on the surface is 42 degrees Kelvin, or minus 384 degrees Fahrenheit. It's cold enough that certain volatiles that were not trapped would sublimate away, but amorphous water ice would not crystallize and would survive over the age of the solar system. So the water ice on Arikoff here has been around since the formation of the solar system. The bilobate shape is the result of a gentle docking between two separate bodies. We see no compression fractures or deformations on the surface anywhere on either lobe, which would be indicative of a higher speed collision. So it's estimated that the contact between these two was no faster than a few meters per second. Or if you were to run into a wall, it would hurt your nose, but that's all the faster these two objects connected. The two lobes are unequal in size, but they've retained their basic shape since they formed. And they formed probably by slow pebble accretion. Slow pebble accretion is back when each individual particle started accumulating, then some of these particles would get together and make a larger particle, and the larger particles, slowly this lobe and this lobe would form. And they would orbit around each other, and over time, they merged into this little docked bilobate shaped pattern. If things were going at a much higher speed, the accretion rate of hundreds of meters per second, we would have more of a potato shape. But since we're at low velocity and it's gravity driven, we get the bilobate shape here. Again, if the two main bodies were going too fast, we would get a very distended object. This is a model here. If we were going about 5 meters a second, it would be this merged potato shape. And at 3 meters a second, the model says this is what we should expect to see, and that's what we have. So the old view of MU69, when we were first approaching it, said we have two globes here that merge together. But when we passed it and looked back and saw the crescent shape, we discovered that actually this is more of a flat pancake, and this is kind of a squashed walnut. The only things we've seen like this in the solar system are the ring satellites of Atlas and Pan at Saturn. And I'm going to escape out of the program. I discovered someone had made a 3D model of Arrokoth here. And so I pulled it up to show you guys. I can't put this in PowerPoint and spin around on it, but this is basically what Arrokoth looks like. Okay, back to the program. So Arrokoth is a member of what we call the cold classical Kuiper belt region. This object basically is primordial fossil left over from the original formation of our solar system. It is the building block component of our solar system. And that's our flyby of MU69. However, the mission continues. What's next? Funny you should ask that, even though I can't hear you. We just finished doing the parallax program, where we took views of two stars, Proxima Centauri and Wolf 359, looked at them from Earth and from New Horizons at nearly the same time, and compared the parallax shift of the stars compared to the background stars. This is the largest parallax measurement ever made. Generally, parallax measurements are done from Earth. Earth's orbital diameter is 2 astronomical units, so we can do measurements of how much the nearby star shifts relative to the background star using this formula right here. Distance d, which is the length here, is 1 over p. P is the half angle of the full parallax change of the object. And the resultant distance is in parsecs, which is 3.3 light years per parsec. From Earth's baseline orbit, we can measure out to about 100 parsecs fairly accurately. Beyond that, we need to use other methods to determine how far away the stars and nebulae are. With New Horizons, we now have a baseline of 46 times of 46 AU, which is 23 times larger than the Earth baseline parallax. So we observed each star twice in case there was a flare by either star or if there's bad weather on Earth. There were ground-based observatories, amateur and professional, who were working together with the New Horizons to do the timing of their images so we could compare the two. However, we're so far away, now we have to take into account light time differential in when the light from a star reaches one of the baseline points. So New Horizons is almost 3 light hours closer to Proxima Centauri right now than Earth, and almost 4 light hours further away from Wolf 359 than Earth, which means we have to take images offset from each other to ensure that we're looking at the stars at basically the same time or simultaneously. However, given the error bars and everything, we can actually fudge that to be within a week of the aesthetically purest time. This is the timeline down here. New Horizons took its observation of Proxima Centauri first. A few hours later, we did ours of Earth. Again, we did Proxima Centauri. Then Earth did Wolf 359, and then Proxima Centauri. Then New Horizons did Proxima Centauri. Then the second pair of Earth, New Horizons, Proxima Centauri views. So this is a star map over here. And this is Wolf 359 would be at this point right here. It is the 8th nearest star to Earth at 7.86 light years away. It's a red dwarf star in the constellation Leo and has a magnitude very similar to that of Pluto at 13.5. Proxima Centauri is the nearest known star to our solar system at 4.244 light years away. It is in the Centauri constellation, and it is a distant member of the Alpha Centauri binary star in the constellation Taurus. And it is brighter than Wolf 359 at a magnitude of 12.95. And you can see it's in this star field here. A gentleman here, William Keel of the University of Alabama, SARA Observatory, late last year, took this image of Wolf 359 and what the expected offset should be from New Horizons. The same with Proxima Centauri and the expected offset that we should see. This came in today. This was posted on our website today. This is Wolf 359, Earth and New Horizons. You see how much it's shifted compared to the background stars. And the background stars haven't moved at all. They're still so far away, they haven't moved. But Wolf 359 has definitely moved. So we're starting to see from the spacecraft a different sky than we do here on Earth. Nothing that we can discern from a human eye, but if we were to do astrometric measurements, we would start noticing differences. And this is a stereo pair of Proxima Centauri. Again, if you could do the stereo imaging thing with your eyes, you can see the Earth and New Horizons view here. However, you can download these images as well as the GIF I just showed you earlier at this website down below. So I'll give you a moment if you want to just screen snap that, and then you can go to that website and pull the images down, play with them, do your own little parallax study from the ground in New Horizons images. And again, this just came out this afternoon, so you're seeing it first time here. And with that, I thank everyone for their time. And I'm going to stop sharing now.
Thank you, Mark. That was an awesome, awesome rundown of everything. Oh my goodness. And I think
it's a lot to digest.
It's a lot to digest. I'll open it up, I guess, if everybody wants to unmute, and hopefully not all speak at once, but I think there's a hand-raising feature, or if we can have some sort of decorum as we go through. Mark, do you want to take any questions?
Yeah, sure. Hang on, I was just checking the chat. Okay, so who would like to go first? No questions? Excellent, I've done my job.
Game over. So you said the guide star is Proxima Centauri?
One of the stars that we looked at was Proxima Centauri.
One of the stars. Okay. So as the mission continues, is there a list of the next things? Like, I guess we don't really find any more objects out there that New Horizons could fly by.
We haven't found one yet. We are looking. And at this point, our little telescope on New Horizons is going to have a better chance of detecting something than Hubble will. And the odds are faint, but they're non-zero. So if we do see something, we're going to have a very, very compressed time to prepare our timeline to do the flyby. But we're mentally prepared for that.
Awesome.
Andy, A for the day.
Thanks, Jerry.
Mark,
Well,
I have a comment.
Yes, David.
I thought it was amazing how the occultation group on Earth were able to pick out that shape of a dual lobe shape just from the occultation studies from the ground. I thought that was amazing considering how small that object is and how far away it is.
Yes. I did have one quick question, if possible.
Yeah,
Given the amount,
just like I have a request, if someone wants me to show the next to last slide again.
yes,
Please feel free to go ahead, ask the question. I'm going to just.
okay. Given the amount of data that you collected from Pluto and Arakoth, you said it was in the gigabits.
Yes.
Do you ever expect to download all of that, ever?
Yes. We downloaded all the Pluto flyby data already. It took us a year and a half to do.
Okay.
I believe, I could be wrong, because we've been doing other things now that have taken priority. We should have all of the Arakoth data down by the end of the year or early next year.
And do you actually have a constant link up with the spacecraft, or do you have to basically take time on the Deep Space Network a day a week or whatever in order to be able to do it?
Oh, it's okay. So yeah, we have to schedule time with the Deep Space Network to have communication with the spacecraft. So there's 3 stations around the world. There's one in Goldstone, California. There's one in Madrid, Spain. There's one in Canberra, Australia. And last summer, their summer, our winter, they were dealing with fires down in Canberra. And it was problematic being able to use them, even though they were the best station given their latitude on Earth to view New Horizons. So we have to schedule time with the Deep Space Network along with every other space mission out there. And there's more than you think that are out in the solar system.
I'm sure, yeah.
And we are no longer a priority mission. Pluto we were priority. Now, if there's another mission like Juno or when Cassini was running, those would be priority missions. And there's new missions going out, and those are now priority missions. So we have to take a back seat as to where we get put in the schedule. Our mission operation managers, one of her jobs is to work that schedule out with the DESN so we can have time with the space.
So how does it work with data downloads? You said it's 800 bits a second. You get, let's say, 1 day a week. Do you spend that entire day just downloading data?
We don't get a whole day, but we get multiple days a week.
Uh-huh.
Depending on the schedule, we can have one every other day, or we can have contacts every day.
Okay.
And the time can be anywhere from 4 to 8 to 10 hours long.
Okay, and so I assume there's some form of compression that the spacecraft does in order to download the data so that you can actually get more.
Yes.
Okay.
There's a cat in there.
And
The cat was mine, my apologies.
Oh. Speaking of data, we had a question from Mike in the chat. If you haven't been able to download all of the data from MU69 yet, how did you get your data from your parallax experiment?
That's a good question. We have a group of people who know where the data is written to on our recorder. They know the address on the recorder. And we can tell the recorder to play this address for this set of data and this address for this set of data. It doesn't come necessarily sequentially how it was taken. So we can skip data to go to other points in the chronologically taken order.
Okay. And speaking of skipping data, with the fires and the location in Canberra, was there any data missed, or if there was any transmissions, would they be able to be recuperated?
Yeah, and we do have data dropouts periodically. It just happens. It's part of life. We do not erase the recorder until we're sure we have the data down.
Mark, when you had the MU-69 flyby, I believe you were able to get a temperature reading of the object. How does that compare with the temperature of Pluto? Given Pluto has a thin atmosphere, is Pluto warmer than MU-69?
Oh man, Pluto is just boiling warmer. It's like 10, maybe 15 degrees warmer. So, you just have to wear a sweater there.
Oh my gosh.
This was incredibly interesting. Thank you so much, Indy.
Yeah,
And
sure, David.
I did have a non-science question for you.
Okay.
Did you make Brian May play guitar at all in the office?
I did not. He was never in my office. We did chat with him and hung out with him for a while in the mock. On a previous visit during the Pluto flyby when he came by, some of the science team who do play instruments did have a small jam session with him. So that was kind of cool.
I was curious.
I got an opportunity after the Arikoth flyby to sit down with him and a few other people and actually talk science, which was kind of cool. And I have to say, Brian May is probably one of the softest spoken, very laid back, very unassuming people I've ever met. When he would try to say something and someone else would start talking, he just sat back and waited. And then when there was a moment of silence, he would start to say something. Someone else would start, he'd sit back and wait until he could get his word in.
Very cool. Thank you so much, Indy.
Yep.
How many light hours is the spacecraft away now?
We are about 6.5 light hours away.
So when you want to get data, you have to tell it 6.5 hours ahead of time, and then 6.5 hours later it arrives on Earth.
Yep. Yep, exactly.
That's a lot of planning.
That's what we call a round trip light time, a 13-hour round trip light time. And we have to also know where the spacecraft will be in 6.5 hours when we send the signal to tell it where to talk to us.
Another question from the chat from Guy. Can you talk about the computer systems on board New Horizons? Is it running, he didn't say this, but is it running Windows 98?
I don't know what it's running.
Or what other computer systems are on board?
I do know there's a PS2 on board. That the processor for a PS2, that we have one of those on board.
Oh, you're being serious. Oh my goodness, really?
Yeah.
That's awesome.
What we're using is stuff from early 2000s, and okay, yeah, Windows 98 was around then.
If Vista would have been, I didn't know at what stage in planning, since before the mission's launched, you put it all together.
Well, yeah, but it's already outdated from what we use in our everyday life by the time we're starting to build the mission, because we have to have it, radiation hardened and verified that it can function in the environment of space. So already the technology is behind the times as soon as you start building it.
Oh my goodness, that's awesome. Another question from Mike. What are you hoping to see next?
Whatever star we come across on the left, and straight on to morning. No, but again, we hope that we will see another MU-69-like object in our flight path and be able to do a flyby. We don't have a lot of fuel left on the spacecraft, so our trajectory maneuvering is very limited as to where we can redirect the spacecraft. So it'll have to be pretty much right in line. We're already most of the way through the Kuiper belt, so pickings are starting to get slim. Meanwhile, we will study whatever Kuiper belt objects are around us as we fly past them. And by flying past them, I mean they're millions of miles away, but we're still seeing them.
When do you start the Oort cloud project?
Funny you should ask that. We're actually discussing an interstellar probe mission at work right now.
Another question, how did you get into all of this? You've been working with JPL, Applied Physics Lab, NASA. How did this sort of start? Were you involved in the construction of the spacecraft or the dreaming up the mission?
We could have gone much further back in time on that one, and then I would have had to blame the guy in the green shirt. I was brought, after I graduated college, okay, let me just go all the way back to the beginning. Eighth grade science. Jerry Jividen there in the green shirt was my 8th grade science teacher. And 8th grade earth science, we studied astronomy, meteorology, and geology. And the first week was, we started doing astronomy, and it was just, that was where I was going. I knew it. And I got a telescope. I started studying I read every astronomy book there was to read. And in the spring, we were in the geology.
Mark, why don't you tell them how you broke the Hubble Space Telescope?
In the spring, we were studying geology, and I was outlining a chapter along with all the other students. And Jerry Jividen, along with the other 2 science teachers, started asking people what they were going to do for a living when they grew up. And he looked at me and says, "What are you going to do, Kochte?" And I said, "The astronomer." He said, "No, you're not. You're going to be a space ranger." And I decided I'm going to be an astronomer. So I went to school, got a degree in astronomy, and then I parked cars for a year. And a friend of mine who was a graduate student in the astronomy department said, "Hey, the Hubble is looking for some people to work there." Hubble hadn't launched yet. It was still 2 years out to launch, but they needed people to work there. So I applied. A few months later, they pulled me in. So I started there. After Hubble, I worked on the FUSE mission for a short while, which is the ultraviolet space telescope, which was also dying. So I learned how to control a space telescope with only 1 gyro. It was a pain. I cried a lot trying to schedule it and not make it safe. And then a friend of mine was working on the Messenger mission, which was going to Mercury. So it was already in space, hadn't got to Mercury yet, and said, "Hey, we need people. Are you interested?" I said, "I'm down." Turned out the Messenger mission and the New Horizons mission are brother-sister missions, and we worked in the same mission operations center. So when Messenger was wrapping up in 2014, the mission operations manager, who was also our group supervisor, just transitioned me onto New Horizons. So I got on about a year before the flyby, and I've been there since.
Just in time.
Just in time.
Mark, when you are transmitting data and your signal, is it disrupted by any solar activity? We're kind of at solar minimum now, but if there's sunspot activity, does that disrupt your signal to any extent?
It can, and weather on Earth can disrupt our signal too.
Okay.
Which is why we don't delete the data until we are sure we have it all down.
There's a tremendous amount of mathematics going into just a simple request.
Yes.
Mark, there's a question in the chat from Angelo. How did we know enough to suggest the Kuiper belt when nothing till then had been discovered from the Kuiper belt?
Gerard Kuiper was postulating, well, he was examining how the solar system was, as we knew it, was formed, constructed, rocky worlds, asteroid belt, the gas giants, and this odd planet out there, Pluto, that didn't seem to match anything else. And he came up with the idea that beyond that point, since we haven't detected anything, there's probably an area, a debris ring area out there, like the asteroid field, and it was called the Kuiper Belt after that. Actually, there's another gentleman who also came up with the idea with him, but Gerard Kuiper was the one who really put forward the idea, and his name stuck to it. I can't remember the other gentleman's name right offhand.
Well, it wasn't Mickey Mouse. Any other questions? Does anyone want to chime in, or if you don't want to speak, if you want to put it in the chat? Obviously, we're sticking around for just a minute. It's about 8:45. Well, before anyone goes anywhere, Barb, do you want to fill us in on the upcoming happenings with the club?
Okay, first, Becky, who's been online with us, she's a relatively new member of the club. She's a pastor at the New Bethel Church in Kempton, and she's gotten approval for us to have a club Star Watch at her church, and that will be on July 17th, the rain date July 24th. And if Berks County has gotten into the green zone, she will be inviting her church members to attend. This one isn't open to the public, but she will be inviting the church members. Now, we will be requesting people to bring a mask. When we're looking through the telescopes, you're kind of breathing on everything, so it would be appreciated if you use a mask at that time. But if you're outside and keeping distance, you probably don't need to leave the mask on all night. So that will probably start around sunset dusk. Then we have a solar program, and I'd gotten the dates confused, so it actually is July 11th from 11 to 12 o'clock. It's at the Colony Park baseball field in Wyomissing. And as we get closer and find out that it is still going to be held, I will send out all the directions and reminders. That basically I give a little talk about the sun, and then we'll do some solar observing. And then we do have a Star Watch on August 21st with the rain date of August 22nd at 8 o'clock. And that's going to be at the Shiloh Hills Park, where we've had Star Watches before. And I will, put directions for that when time comes closer.
Awesome. Well, thanks so much. Of course, the radio station, I'm going to try to bring them into the things that we can. Obviously, it would be only if things are safe and everyone is safe as well. So we'll make sure WEEU has more and better space information. I have some Pluto notes to bring back to them, since they always like to jab with every caller who has a space question. Do you think Pluto's a planet? And so now I have a couple more answers and some more information. So thank you, Mark, for hosting this, joining us. We'll have a meeting next month, second Thursday as always, at 7:30. But just we'd like to really extend a thank you to you. And another question that we had coming in, where will the Zoom meeting be posted? We'll definitely make sure we link to it through our social media accounts, Facebook, whatever there is on Twitter, I guess, through the email list. We'll find a way to put it together. But if you have any other questions for the Astronomy Club side of things, berksastronomy@gmail.org is one way to reach us, or berksastronomy.org, gmail.com, berksastronomy@gmail.com, or the website berksastronomy.org. And then if you have any other further questions for Mark, we can forward them along or follow along with the New Horizons mission. Thank you, everyone, for attending this. This is awesome. We had some really great questions at the end, and the presentation really is cutting edge. We saw pretty much live New Horizons data. So, I mean, that doesn't get better than that. So thanks to everyone for joining. And with that, I hope to see you more and share more about space.
Thank you kindly, Mark.
You're the most welcome.
Thank you very much, Mark.
Thank you.
Thanks, Mark.
Maybe just one final question, Mark.
Certainly.
You have access to a little more technology than I do. How do you get that phenomenal background behind you put on the screen?
Well, it's actually Zoom allows
Really?
me to change the background.
Oh,
Yeah, if you click the little dots on the top of it, it'll come up and it'll say virtual background.
Virtual background. Okay, I'll have to play with that a little bit.
Yeah, on my screen, down at the bottom, I have a thing that says video or stop video, play video, stop video, and a little up arrow caret next to it. If I click on that, then a pop-up menu comes up and it says choose virtual background. And then it has a handful of preloaded images, and then you can also load your own images in.
Oh, that's beautiful. Very nice.
So those are a couple of my images.
The mission might be working on Windows 98. I'm still on Windows 3. So
I actually work on a Mac. But we do a lot of our work on a Unix box.
Yeah. I actually like a Mac anyway.
I do everything on a Google Pixel phone. So
you'll have to excuse Alon a little bit tonight. He's still flying high from watching the launch last week at the space.
I would be too.
Yes.
Oh my goodness. I don't know how we were able to pull it off, but I'm here at my desk, and I was supposed to call into the radio station, do like 20 minutes on the SpaceX Crew Demo 2 mission, and I'm on the phone. They put me on hold. I'm on the line. People are asking questions. I'm talking to the guys, and more attention was given to this thing. And I was scheduled 2 hours before the launch to just give a little blip about it, and then leading up to the launch in that 20 minutes. Well, I spend 3 hours going through this, the launch scrubs. During a commercial break, I drive to the radio station, jump on air, and then I get a call from the owner of the radio station, and I'm like, I'm on air, I can't talk right now. And so I end up getting back to him. He texts me, don't get excited and all, but do you want to go cover the rescheduled launch date down in Florida? And of course, that's like a dream come true for me. I've never seen a rocket launch live. I'm excited about everything space, and I'm digging more into like the commercial space race, and why didn't I like pay more attention to all the shuttle launches back in the day? And as a younger guy, I didn't have a space race. So this is my space race, and now I'm just sort of snowballing more and more. And as I get better at recognizing things with astronomy and just all the science and research that goes into it, I'm finding that I'm sort of drawing back from knowing everything about one particular item and just trying to share it more and more. And so that led to my work in a planetarium, that led to my work with the radio station. And when things ease up, you can find me outside with a telescope on a street corner, probably in a downtown area.
Very cool.
Yeah, so it's all about sharing the love of space and everything that comes with it, from rocket launches to like high-end telescopes to robots that we fling out from the sun. So it's super cool.
I also think the collaboration between SpaceX and NASA, and probably the upcoming collaboration with the Blue Origins, is that the one it's called, Lon? And
Yes.
NASA. I think that's going to bring a lot of cool missions coming up, and a lot of different ways to get things into space for more research.
Yeah, Blue Origin is sort of this resting giant right now. I was surprised when I went to the Kennedy Space Center Visitor Center. Right across from the entrance, we were all waiting in line for the gates to open at 9:30, and behind me in the rear view, there's this giant rocket factory that says Blue Origin. That's bigger. I think it's bigger than the Kennedy Space Center complex. It's huge, and when NASA starts pulling them into action more and more, and over these years, hopefully we see some awesome missions with them. SpaceX is sort of the build, test, fail, retest, build. I don't know. Their cadence of putting things out is a lot faster than everybody else. But Blue Origin, I'd love to see more from them. It seems like they've snowballed a few companies together into some of their proposals for the moon missions for the Artemis program. But we'll see more to come with that. I'm loving the background that Mark has there. Is that the inside of the shuttle?
No,
No,
Where are we?
Falcon.
that's, yes, I was going to say.
Oh, that's in the Falcon?
Yes,
The Millennium Falcon.
Millennium, not the Falcon 9, silly.
Yeah, I've been staring. I got confused for a second. I've been staring at the Crew Dragon module way too long.
You look just about as good as Harrison Ford does, Mark, so you're all right.
Yeah.
I was waiting for Chewbacca to pop up.
Well, awesome. Oh, I haven't even seen. We have a ton of thank yous in the chat, just left and right, up and down. Thanks everyone. Thanks. That was great. Enlightening, super. Yeah, that was awesome, and thanks for joining us here.
Yeah, thanks everyone for coming. And
Oh, how can we? Where else do we get information? It's less than 24 hours old. That's phenomenal. Thank you so much.
Yeah. Is it publicized, or do we have access to anything?
The website that I showed is the public access website.
Okay, awesome.
Okay.
All right. Well, I think that about does it. From here, so I'll start firing up the stove. But thanks for joining. I'm going to sign off as well. We'll be in contact, I'm sure, and we'll go ahead and share this to wherever we can, really.
Yeah, as soon as I get it finished up and processed, I'll get a copy sent to you.
Awesome.
Thanks for the great work, Mark. Good luck in the future.
Thanks, David.
Yeah, thanks for everything you did to help set this up for us.
Thanks, Barb.
Amazing presentation. Thank you.
Yeah, thanks, Becky.
All right, and we'll check back with the New Horizons mission as things roll out. I'm sure now that I have your email, I'll be shooting you some questions. And
more than welcome to.
Thank you so much.
If I don't answer right away, just ping me another day. That, hey, I sent you an email.
Yeah. Awesome. All right. Well, thanks.
Have a good night, guys.
Good night.
Good night.
Night.
Good night.